the student may find it remarkable that this elementary analysis of this most basic of chance experiments is actually of very recent vintage. A study of coin tossing along these lines was published by J.B. Keller in the American Mathematical Monthly as recently as 1986. Quo vadis? Latin for, where do we go from here? It would be as well to step back to get a bird's eye view, as it were, of the larger province of natural problems that lie within the scope of such investigations. Now, to begin, a student might say, well, what if we alter the conditions of the coin-tossing experiment? The student may well be willing to believe that if the coin were allowed to bounce instead, that nothing essential changes in the analysis. And if she has some algebraic dexterity and a little knowledge of physics, she might well be inclined to try the analysis herself. The conclusion remains the same. Under most normal conditions, the toss of a coin appears to have a random character. The early uncertainties tend to get washed away in the process of actually tossing the coin and capturing it. At a larger remove, one could ask, what about other physical dynamical systems? Does chance arise naturally in such settings as well? Now, let us begin again with a historically important example, but one which has been made familiar by Ian Fleming's intrepid protagonist James Bond in his fondness for the game of roulette in gambling casinos. Here's an image, an 18th century cartoon of a roulette wheel. And here is a modern roulette wheel. Now, the actual mechanics of the game are not important for our purposes. All that matters is that one has a wheel which is spun, and a ball spins around the wheel and settles somewhere on its periphery, and the gamblers bet on the location the ball ends up in. Okay. Now, if one was a gambler, if one were to go to a casino, then one would like to have some kind of assurance that the wheel were fair, that the croupier could not, by sleight of hand, affect where the ball would end up on the circumference of the wheel. Is that really the case? An analysis of this problem was actually undertaken just over a century ago in 1896. And if you're like me, you like to get a flavor of what the time was at that time. This is an image of Paris in 1896. It's due to Edmond Grandjean. It's Laplace cliché. And here's another image of Paris at that time, Saint de Rue à Paris, due to Maximilien Luce. The year was 1896, little more than a century ago. It was a time of handsome cabs, top hats. It was a time of empire. But the mathematical problems were in a sense the same then as they are now. An analysis of roulette was undertaken by Henri Poincaré, who at that time was teaching at the Sorbonne in Paris. And here's an image of the Sorbonne. This is actually a 17th century image before a famous fire at the Sorbonne, but presumably in the late 19th century, the Sorbonne had not changed in essence. This is the University of Paris, the Sorbonne. And while Poincaré was there, Poincaré was a noted topologist, a man of many parts. And while he did not publish in the theory of chance, he actually taught a course in probability. And he must have been a remarkable lecturer, because among the many problems he analyzed was the game of roulette. And his lectures were published in a book in 1896, the Calcul des Probabilités. It's a beautiful little monograph. If you're curious, you can get it online for free. And it's a wonderful historical object and also beautifully written. The problems are engaging, and they illustrate a probabilistic mode of thought in the most prosaic problems. And this way of thought turned out to be very, very powerful. Now, Poincaré's ideas on roulette could be used in other settings. What other kinds of games of chance, what other settings in practice do we see where chance arises apparently inevitably as part of the process? But these are, in essence, physical systems. For example, one can think of the game of billiards. Many balls on a tabletop. One hits a ball against other balls, the balls scatter. Where do the balls land up? This is a completely deterministic problem, just as the roulette wheel, where given initial conditions, one knows exactly, in principle, where things should end up. But of course, with many balls, even small variations in initial conditions cause potentially dramatic changes in where the balls end up. Now, if one goes to a larger scale, if one imagines, let's say, a room, and instead of billiard balls, one has, let's say, atoms or molecules interacting with each other, bouncing off each other, then again one ends up with a deterministic system which is well described by a stochastic law. At the atomic level, this was famously done by none other than the luminary Albert Einstein in the year 1905, the Annus Mirabilis, where the 4 papers of Einstein changed the world. In one of them, perhaps the least heralded of them, Einstein talks about how to measure Avogadro's number. The student might remember Avogadro's number from our basic chemistry classes as representing the number of atoms in a mole of gas. How does one measure this mystical quantity? Einstein proposed a methodology where he imagined many atomic particles interacting with each other according to a common stochastic law. Today we call that Brownian motion. Now, based on Einstein's paper, J.B. Perrin in Paris, 3 years later in 1908, conducted very precise experiments which resulted in very accurate measurements of Avogadro's number. Today, it's about 6.023 times 10 to the power 23. Perrin's labors resulted in his getting a Nobel Prize. So there's actually rewards in this game as well. Moving on, if one moves from the game of billiards, imagine throwing a dart at a dartboard. Again, the outcome should be completely prescribed by the initial conditions, completely determined by the initial parameters, speed, velocity, direction, and so on and so forth. In practice, there is uncertainty in where the dart actually ends up. If there were not, darts would lose its appeal, would it not? And again, we have a deterministic physical system with apparently a random component. Pendulums on a swing where various parameters are uncertain. For example, the masses, the lengths of the cords, the speed at which they were sent in oscillation, the elasticity of the cords, games of dice, blocks on springs, and, of course, inevitably, the toss of a coin. And if we go clockwise around from upper left, what I've shown you is systems of decreasing complexity, but all of which seem to have ultimately a chance-driven element to it, though all of them are at heart deterministic, physical, evolving systems. Now, Poincaré's idea turned out to be very, very powerful. It was built and expanded on by Eberhard Hopf in the 1930s and given the evocative name, the principle of arbitrary functions. Now, what this is intended to communicate is that the initial conditions, parameters, elements that make up a physical system have some uncertainty in them. The uncertainty might vary from instance to instance. But no matter what the initial uncertainty is, the outcome always seems to be regulated according to a common stochastic principle. And therefore, since there is no dependence on an arbitrary initial condition, this entire body of ideas is called the principle of arbitrary functions. We could summarize this principle loosely, but the gist of it is clear in these lines. Uncertainties in our knowledge of many dynamical physical systems tend to wash away as the systems evolve. In the long term, all these uncertainties morph into a common stochastic description of how the system is evolving. And thus, regardless of the initial speeds that we impart and the variation in individual speeds from individual to individual, at the end of the day, the result of the toss of the coin is a fair coin. It is unpredictable. About half the time one gets a heads, and about half the time one gets a tail. This lecture was intended to show that even commonplace physical systems could be suitably modeled by chance phenomena. Of course, if one goes down to the quantum level, then chance is inescapable. Chance is part of the fabric of particles at a quantum level. But even at macroscopic deterministic physical levels, chance appears to play an ineluctable part of the system. In our next lecture, we'll now move on from the fabric of probability, the axiomatic foundation, to the next step, where we ask, how does one incorporate evidence that is obtained in the performance of a chance experiment, evidence, information on the side about the outcomes that arise? How can one incorporate in a very systematic way such external information into the probabilistic framework? This will lead us to the important idea of conditional probability.